Hey yo, what's up, YouTube? It's your boy JOSHABRAHAM. We're back. We're back. Live and strong. So, it was the ebullioscopic. I should have started time for 30 minutes. The ebullioscopic method was applied for determination of the molar mass of an unknown organic compound prior to the determination of molar mass. The ebullioscopic constant of the solvent carbon tetrachloride was quantified by the boiling point elevation technique with naphthalene. So the solvent is carbon tetrachloride. Boiling point it was elevated using naphthalene, and we have an unknown organic compound. The boiling point of solution of 304 milligrams naphthalene is 26.6 grams of carbon tetrachloride. Wait, this many milligrams of naphthalene in this much carbon tetrachloride is 0.455 degrees higher than that of pure carbon tetrachloride. Pure carbon tetrachloride is 7. So it's gonna be 77 degrees something. 80, 20, 350 Kelvin. Okay, so it's about 350 Kelvin after the boiling point is elevated. Now the molar ebullioscopic constant of the solvent. What is that? It's absolute cinema. um, there is a formula. I forgot. People, I know what you're thinking. Like, oh, this guy is doing the assignments now? That's too late. I know, but let me see how fast this guy up here works. I need to test his capabilities. I believe it's a pretty good organic stuff up there. Let's see. The molar ebullioscopic constant of the solvent. The molar heat of evaporation of carbon tetrachloride. Then the boiling point elevation of carbon tetrachloride was determined as a function of molality of the unknown substance in an ebulliometer. In every experiment, 96.8 grams of carbon tetrachloride was used. Additionally, elementary analysis was performed, and weight of carbon is 10.13 weight percentage. Weight of chlorine is 89.87. Okay, carbon tetrachloride. I mean, of course, it's tetrachloride. Makes sense. Determine the molar mass, some formula name of the unknown substance. Okay. So can we ebullioscopic constant I do remember we have to find the molality. What happened here? Like, what is wrong? You know what? Yeah, this one's pretty old. Oh, okay. Okay. Where's my OG? Did I delete the OG? What? What? This is the problem. If I look at the keyboard, I cannot see what's happening on the screen. Stop. Stop. Anger. Anger is useless. It's useless. Sometimes DeepSeek just works. And there's this stupid. Oh, make sure you don't. Come on, come on, come on. What? Moles of solute per kilogram of solvent. Moles of solute per kilogram of solvent. So moles of solute, we have to find the moles of naphthalene with a kilogram of solvent. You just convert this to kilogram? Is that what it is? So what it is? Solute of calibration, naphthalene. Solvent mass, boiling point of elevation. Okay, it's the elevation. Okay. Unknown soluble data masses and dB given. Elementary analysis. Okay. Part A, determine the molar ebullioscopic constant. The formula for boiling point elevation is boiling point elevation, ebullioscopic constant, molality. So we first calculate the molality. It's the grams divided by what? Oh, first we're finding number of moles of naphthalene, and you just convert that to kilograms. That's it. Find molality, and you find the ebullioscopic constant. Okay. That's first one. Now, molar heat of evaporation. Determine the molar heat evaporation of carbon tetrachloride. We use the formula. Oh, that's a pretty good one, eh? That's a pretty good formula. Where R is 8.314 joules per mole Kelvin, TB in Kelvin 76.7 plus 273.15. Wait. Determine the molar heat capacity of heat of evaporation, H vaporization of Kelvin. So this is the formula you're using, where universal gas constant multiplied by elevation of boiling point square by what is M, molar mass of the solvent. Rewrite that. Determine molar mass of and the formula of unknown. So we use the same formula and rewriting the moles. Rewriting for moles. Okay. And example calculation of with the first data point. Do the same for it should be consistent around 240 grams. Determine the molar formula for elemental analysis. Wait. I remember my professor or the tutor letting me know that it's gonna be exo. There's gonna be exo sheet involved. 25, yeah. So to plot perfect for part C, your tutor wants to plot mass. Calculate them for all experimental points. What are these experimental points? Bim. How do you plot? How do you plot this? What's this? Boom. Exactly, that's the method your tutor described. Here, so break down what you do. Using your experimental points of m calculus, extrapolate the lines back to m equals 0. The intercept at m equals 0 gives the true molar mass of the solute, removing any experimental errors from concentration effects. Relate the boiling point elevation to molar mass. M is molality. Okay, we rewrite the equation. Now then, the molar mass of the solute is number of moles or mass of solute. Okay, mass of solute by number of moles. Wait, number of moles is given mass. Number of moles is given mass divided by molar mass, right? This is the mole. This is the number of moles. Number of moles equals given mass divided by molar mass. So molar mass. Okay. Number of moles can be changed to this. So the given mass of solute divided by molar mass, given mass of the solute divided by given mass of the solvent. Why is it kilogram? Why? KB, okay. Calculate M for each experimental point. Mass of solvent, I think we have it, right? M values are slightly different due to the experimental errors, but mostly around 240. 240. Plot M versus M. X-axis massive solute. Draw the points and extrapolate line to M equals 0. Intercepts give 2. Determine the molecular formula, elemental analysis, empirical formula. 1:3. Is it 1:3 though? It's 1:9 or some shit. If you ask me, or 10 divided by 90. 10 divided by 90, 1/9, yeah? What? Boom! One's here, one's here, one's here, one's here, one's here, one's here. I thought the blue points should be in this. I see the confusion. The blue point represents your experimental data, which may scatter slightly due to the measurements error. The red line is. I don't know. It says. What? Is that how it goes? I mean, this part, it's just. .240. Okay, 0.0.05. Okay. It's 240 and 246. 247. No. Yeah, 247. 2.6, yeah. Okay. I don't know. From the looks of the graph, only 1 point is passing through the red line, which is 247, 2 points. Others are not even close. Okay, so this is more like mm-hmm. Two 52. Okay. $30. Okay. Let me take. Let me. Uh, okay. Can you can you again explain why you to chose the graph to find I I wouldn't have that matter of fact I wouldn't have proceeded this. So what made plot the graph what made you plot the graph so that we'll get the we want molar mass of the unknown solute From the bilioscopic method, the formula, yeah, I understand that. So for each experiment, each solute, now we're talking solute. So here the solute is, we can calculate experimental molar mass. Experimental molar mass of what? Why a graph is useful? Wait. What was I thinking? Yep. Got him. Why is a graph useful? In the real experiments, delta t measurements are not perfectly precise. Where is delta t? Okay. As m equals 0, very dilute. Could you explain? explain what like I'm pretty confused on the solute part because we have NAF solute. So molar mass is one mole mass of 1 mole of substance. Example 2, naphthalene, 1 mole of naphthalene weights, okay. So molar mass tells how many grams corresponds to, Why we talk about the solute? In colligated property experiments like ebullioscopy, the solute is the substance dissolved in the solvent, okay. The boiling point elevation depends on the number of solute particles, not their type. Ah, okay. For example, first we use naphthalene as standard solute to determine the kbf. Later, we use the unknown solute to determine its molar mass. So these are two different solutes in your problem. Used for calibration to find Kb. Mass of solute, you're analyzing naphthalene for calibration, unknown part of C. Step by step, calibrate Kb. Use naphthalene's no mass to. Okay, so we're Kb is ebullioscopy constant. Yeah. Determine the unknown molar mass measured. Use Kb from your already found. Calculate M for each experiment, each solute mass, plot M versus M, extrapolate to get a reliable molar mass. In short, solute just means the substance you dissolve in the solvent. It can be known naphthalene or unknown your target compound. This process is the same. What changes is whether you're using it to calibrate Kb or to calculate inner molar mass. Calculate molar mass. What's inner molar mass? Think. So we find the ebullioscopic constant using the known solute naphthalene. Then I guess the ebullioscopic constant remains same for CCl4. Then we plot the with molar mass of solvent. And didn't get how the molar mass was then obtained after this graph. You're on the right track. Let me explain step by step, clarify each step how the graph moves. Graph gives the smaller mass. Use naphthalene, which has a known molar mass of solute. Dissolve a known mass of naphthalene in CCl4. Measure boiling point elevation, molality. My hands are cold. What? Especially the right hand. Because when I do this, I feel cold on my left hand, and when I do this, the behind of my left hand is feeling cold. Feel me? I can literally. My left hand is feeling cold. That means my right hand is the colder one. That's so weird. That's so weird. Why is temperature different? I know. This all okay. Now you which is a property of the solvent. Okay, so it's a constant value for tetrachloride. Use Kb with unknown solute. Each solute gives a different molar. Solve unknown solute and measure Tb for different solute masses. Each solute mass gives different M because experimental errors affect delta Tb. Molar mass of the solute at very low solute mass, the solution behaves ideally. I'm still a bit confused. What are these numbers? What are these? You're plotting M here. Molar mass, M is the molar mass of the unknown solute that we're finding using, okay? Mass of the unknown solute added in each experiment. So we're adding this value to a fixed amount of carbon tetrachloride. Mhm. We add more of the shown, which results change in usually but the more the higher does change in temp. What was smaller mass? The molar mass meaning you don't see shit. Why boiling point increases with more solute? This is colligative property. Yeah. Boiling point always increases when you dissolve non-volatile solvent. The positive, yes, BP doesn't increase, but it rises because solute particles reduce the solvent's vapor pressure, requiring higher temperature to boil. Okay. Now, why the calculated molar mass changes the formula of molar mass? How much solute you added? Important. What for each experiment? Okay, this is more like an experimental molar mass. Okay. Experimental errors, non-ideal behavior at higher concentration. Okay, you know what? I'll be right back. I'm living in the 21st. Doing something mean to it. So I have to head to university in about uh 3 hours. Yeah. Because I have that meeting with the student union. Student union meeting. Meeting. What else? Submit the sequence analysis. Oh shit. Tomorrow I have presentation. I might have the presentation. Mm-hmm. Mm-hmm. So if I'm having a presentation, that means if I'm answering, I should know exactly what I'm saying. Each experiment gives, okay, how the graphics is this a plot? Intercept gives the true molar mass. I don't think. I don't know. For me, it's just the m equals 0. I don't get that one. He's understanding your start from the basic formula for boiling point elevation. Here, m here is the molality of the solute. M equals n of solute by m solvent. Rearranging for experimental molar mass from the measure delta Tb. This is the molar mass calculated from one experiment point. It assumes the solution behaves ideally, meaning no solute solvent or solute solvent interaction beyond the basic colligative effects. What happens at higher solute concentrations? What happens? I don't know. Focus, focus. For boiling point elevation, Rearranging, yeah. Right. Here, calculated m depends on, but at finite solute mass may slightly lower than ideal due to the interactions. Take limit. I mean, this limits. It's goddamn limits. I never expected limits to come up here. The intercept of an exaplated m equals 0 gives m true, the molar mass. Think of it like this: high solute mass, interactions, experimental errors, noisy m values, okay? Extrapolating 0 solute mass removes the effect of errors, you get the real. I mean, if m of solvent is 0, if m we have a 0 at the denominator, the numerator, like that just don't make sense. We draw a straight line. No, I still stood how you got a value after considering solvent the solute resulting actual. Can you show me the steps that gets to the answer? What's tipping you up? You hung up on the ID. How can you? You did this for all you guys. Here we are considering the first case, that's the lowest. Could you explain a bit on how this lowest HIGHEST accuracy for yes, this is important part of the colligative property experiments like ebullioscopy. The key idea is why smaller solute masses, more dilute solution gives more accurate molar mass values, relations between delta T. Just a minute. What? Oh shit. Okay. Focus. I got a class at 3:30. Uh, why this gives me ideal behavior at low concentration. So, if we want again ideal behavior, how this ideal behavior relates to actual concentration. What gives at higher solute mass, smaller interacts with a small deviation for ideality. Low solute mass interactions are negligible, barely calculated m is closer to true molar mass. Ideal behavior at low concentration at higher solute mass. Molecules interact with each other. Small deviations from ideality calculated m can shift up or down at very low solute mass. These interactions are negligible. Delta T accurately reflects the number of solute particles calculated. Okay, this was the part I was a bit confused. So, lower concentrations uh, acts more ideally, but how is the cons affecting the molar mass? It should always stay same from what I have understood on molar mass. If everything were ideal, there were no errors. Every point would give the same molar mass. Why calculated m changes with concentration? For formula assumes ideal solution behavior, meaning the solute doesn't interact with itself or solvent beyond basic colligative effects. At higher solute mass slash concentration, solute molecules interact with each other, slightly lowers delta T compared to the ideal linear prediction. At very low solute mass concentration, molecules are far apart. Solution behaves nearly ideally. Definitely not Toby Fox. Greetings. Greetings, fellow human beings. I appreciate definitely not Toby Fox for definitely checking out the stream. You see what I did there? uh, Meaning the solute doesn't interact with itself or solvent beyond colligative effects at higher solute mass or concentration. Very molecules are far apart. Solution behaves nearly ideally. Delta B matches theory. Again, I how does low solute concentration? Again, can you explain how does low solute mass accurate Can you explain what is happening internally and how it favors for low mass of solute to have inside the solution and why solute mass gives a more accurate molar mass. This is about ideal versus non-ideal behavior. It's easier if we think molecularly. What ideal solution means? Ideal solution is if solute particles don't interact with each other. Solute particles disinfect solvent molecules beyond the basic colligate effects, like lowering vapor pressure. In an ideal solution, delta TB is strictly proportional to molality. 26, god damn it! YouTube. I'm gonna end the stream, but unfortunately, I will be doing this in my tablet during my classes. Did I just? Oh, no, don't worry. So I'll be doing that, and I'll be writing the answer to this question and one more question. Also, oh shit, I gotta do my I gotta go to the meet. Well, you too, peace out.